All right, welcome everybody. So in this video, I want to continue working with inner product spaces, but I want to extend our study beyond R2 and R3 and Rn and apply this to more general vector spaces. In this video, we'll take a look in a second at a polynomial vector space. But let's just let V denote any arbitrary vector space, and we have some inner product that we've defined on V. So V is an inner product space. So given any vector inside of this vector space V, because we have an inner product, we can now define the length of these vectors. So for example, if V is a polynomial, we'll be able to measure the length of a polynomial by taking the square root of the inner product of V with itself. And recall, because this inner product satisfies the four required properties, one of them says that the inner product of V with itself has to be greater than or equal to 0, that we're fine taking the square root of this inner product. Oftentimes we'll write this as the length of V squared is equal to the magnitude of V with itself. So, so far we can see that there's only one vector that would have no length, and that would be the 0 vector. That seems like a pretty desirable property to have in our geometric space here. We would like the 0 vector to be unique in the sense that it's the only vector that has length 0. We have many unit vectors, so any vector whose length is exactly equal to 1, that's what we're going to consider a unit vector. And recall, finding unit vectors, particularly with bases, is really nice. We can find the distance between two vectors, u and v, and now we're using the term vector more generally. We're not just restricting ourselves to column vectors. The distance between these two vectors we can compute by taking the magnitude of u minus v. So in other words, here what we mean is we take the square root of the inner product of u minus v with u minus v. Okay, so we can measure lengths of vectors and distance in our vector space now, in any vector space. And lastly, for angles, for example, if I want to determine whether two vectors u and v are perpendicular to each other, whether they're orthogonal to each other, we're going to say that two vectors are orthogonal if and only if the inner product of u and v gives me the scalar 0 back. So once we have a vector space and then we give it an inner product, that means now we've got a geometry, we've got lengths and distances, and pretty much everything that we've discussed about orthogonality for vectors in Rn is going to carry over to more general vector spaces. So we've talked about why it's really nice to take some of these more abstract vector spaces and give them a basis. Moreover, now that we've got lengths and distances, we can take any vector space, and if we have an inner product, then we're going to be able to find an orthonormal basis for that vector space going through the Gram-Schmidt process. So let's take a look at an example on the next slide. Okay, so the example I want to consider is, let's consider the vector space P4. So we've got the usual addition of vectors and scalar multiplication, but we're going to define the following inner product on P4, similar to the way we defined an inner product earlier on P2 by evaluating these functions P and Q, in this case at 5 different values, at -2, -1, 0, 1, and 2. So there's nothing special about the values -1, -2, 0, 1, and 2, other than they're pretty small and simple to work with. But we could have chosen any 5 distinct values, and that would give us a different inner product, but we would have an inner product space nonetheless. And so this vector space P4, we have a standard basis, which would be consist of 5 polynomials, the polynomial 1, t, t squared, t cubed, and t to the 4th. So taking any linear combination of these vectors, we can generate any polynomial at most degree 4. So what we're going to want to do on the next slide is I'm going to ask us to compare lengths of some of these vectors in our basis and calculate the angles, or at least determine whether some of these basis elements are orthogonal to each other. So the three that we'll take a look at are the first three elements in our basis. So that would be the polynomial p of t equals 1, q of t is equal to t, r of t is equal to t squared. And what we're going to want to do is answer some questions that relate to the inner product of these polynomials with each other, with other polynomials. So first, I'm going to just create vectors for each of these three polynomials. We are going to create a vector where we evaluate the function at all five of these points. So for example, this first polynomial p of 1, which is the function 1, if I evaluate this function at -2, right, I get an output of 1. If I evaluate it at -1, I get 1. So no matter what value of t I pick, this polynomial is the constant polynomial, which is equal to 1 for all values of t. So this first polynomial has a column vector of all ones corresponding to the 5 values that I would get when I evaluate that function at those 5 values. For P2, we define this as the polynomial t. So if I evaluate this at -2, I get -2. If I evaluate it at -1, I get -1, and then 0, 1, and 2. And then lastly, I'm going to take the third polynomial that we're considering now, which is t squared, and I'm going to create a vector of values that I get when I evaluate P3 at each of these 5 values. So I would get -2 squared, which is 4, -1 squared gives me 1, 0, 1, and 4. And now it's going to be really convenient to work with these vectors, because if, for example, I want to calculate the inner product of 1 with t, you can see that's going to be related to taking the usual dot product of these vectors that we've created by evaluating the polynomials at our values of t of interest. So let's do the calculations on the next slide. So given this vector space of polynomials at most degree 4 with the inner product we've defined up top, so now we've got an inner product space, there are lots of questions that we can ask. So for example, if I want to compute the length of the vector p1 of t, which is just the constant vector 1, then what I would do, by definition, we define length of a vector as the square root of the inner product of that vector with itself. So in this case, p of 1 is the polynomial 1. Okay, and so be careful here. We're not taking the inner product of the number 1 with the number 1, or the vector 1 with the vector 1. This is representing a polynomial. And so to take the inner product of the polynomial 1 with itself, we evaluate it at each of these points at -2, -1, 0, 1, and 2, which is going to give us a value of 1 every time. And now I'm going to take the inner product of this vector of 5 values with itself. So that's going to give me 1 squared plus 1 squared plus 1 squared plus 1 squared plus 1 squared. So I get the square root of 5. So that might seem weird. This polynomial p1 of t, which is equal to 1, you might think that this polynomial should have length 1, but actually its length is the square root of 5. And if we define a different inner product on this space, then it's very possible that we could get a different length, even though we haven't changed the polynomial itself. Question 2 is asking us, are the vectors p1 of t, which is the polynomial 1, and the vector p2t, which is the polynomial t, are these two vectors orthogonal to each other? So be sure that there's a difference in saying whether two things are orthogonal or linearly independent. So these two polynomials are definitely linearly independent. One is not a scalar multiple of the other, but that has nothing to do with whether or not they might be orthogonal. That is a condition that's based on the inner product that we've defined. So let's take a look at what we get when we calculate the inner product of the vector 1 with the vector t. So here we've evaluated the first polynomial at all 5 of these values. We've evaluated the polynomial p2 of t equals t at all 5 of those values. And so now this inner product says, let's take the usual dot product of these two vectors. And so that gives me 1 times minus 2 plus 1 times minus 1 plus 1 times 0 plus 1 times 1 plus 1 times 2. So these negative terms cancel out these positive terms. So the inner product of these two polynomials is 0. So 1 and t are indeed orthogonal vectors in this inner product space. If we had defined a different inner product, for example, by picking 5 different values where we evaluate the polynomials, then this property might change and these two vectors might not be orthogonal with respect to some other inner product. So whether or not these vectors are orthogonal, that depends on the inner product that we've defined. And let's practice one more here. If I want to determine whether the vector p1 of t equals 1 and p3 of t equals t squared, whether these are orthogonal, now I take the dot product of the evaluation vector for the first polynomial and the evaluation vector that we got when we evaluated t squared at those 5 different values. And then we just take the usual vector dot product of these two vectors. And that would give us 1 times 4 plus 1 times 1 plus 1 times 0 plus 1 times 1 plus 1 times 4. So we don't get cancellations here. I forgot a t squared over here, excuse me. So the inner product of 1 and t squared actually gives me 10, which is not equal to 0. So these two vectors are not orthogonal to each other. Okay, so this vector, the polynomial 1 and the polynomial t squared, these are linearly independent vectors, but they are not orthogonal to each other.